So now we are going to discuss about the deadlock detection. So there are two types of deadlock detection algorithm we have. One is the first one is for single instance of resource type. Another one is the multiple instance for each resource. So for single instance of each resource type, the deadlock detection algorithm that uses a variant of the resource allocation graph called as wait for graph. Okay, so we are getting this wait for graph from the resource allocation graph, then by removing the resource nodes. Okay, consider the edge from Ti to Tj in a wait for graph implies that the thread Ti is waiting for thread Tj to release a resource that Ti needs, and an edge Ti to Tj exit. It means that in a wait for graph, if and only if the corresponding resource allocation graph contains two edges, that is Ti to Ti is requesting resource Q and resource Q has been already allocated to Tj. Then only we have a edge Ti to Tj in a wait for graph will be there. Okay. So consider this resource allocation graph. Okay. So in this resource allocation graph we have removed all the resources. Okay. So we get this wait for graph. This wait for graph is the corresponding to this resource allocation graph. If there is a cycle, if there is a cycle in a wait for graph, it implies that there is a deadlock. If there is a cycle happen in the wait for graph like this, okay, so here we have a two cycle. If there is a cycle in a wait for graph, so it is a deadlock. Okay, then we see the several instances of resource type. For this we see this data structures available, allocation and request. So the available is a vector of length m, indicates the number of available resources of each type in the system. Okay, then allocation is an n into m matrix. It defines the number of resources currently allocated to each thread. The request is also n cross m matrix, indicates that the current request of each thread. If request ij is equal to k, then it means that the thread I is requesting the k instance of resource j. Now we see the deadlock detection algorithm. First consider, so there is a work and finish be the vectors of length m and n respectively. So the work is equal to available. Then for I is equal to 1 to n, if allocation is not equal to 0, then finish of I is equal to false. If the allocation is equal to 0, there is no need of, that thread has been completed its execution, then only the allocation will become 0. So if the allocation is not equal to 0, it means that that particular thread not complete its execution. So the finish of that particular thread is equal to false. Otherwise, if it is 0, otherwise it will be true. Okay. Then find an index I such that we are finding that particular thread finish of I is equal to false. It is not completing its execution and it requesting some resources. That requested resources is less than the available resource. The work is equal to available. So the request is less than available. It means that we find those threads and we can allocate the resource to those threads. While allocating, you have to update the work vector. The work is equal to currently available plus allocation. Okay. So once it's complete, the already allocated resources also has to be added into the available. Then you have to make that finish of that particular thread is equal to true. This is after completion. Okay. Then go on, keep on, you have to find those kind of threads and you have to complete its execution. Okay, after completing all, if the finish of I is equal to false in the last for any thread, I is equal greater than 1 or less than n, greater than or equal to 1. If 1 or 2 or n, okay, threads are thread status finish of the thread is equal to false. If it means that the particular threads are not completed its execution, then the system is in a deadlock start. If all the threads are not completed its execution, even one, then the system is in a deadlock state. So by using that, we can find there is a deadlock. Consider the example for deadlock detection algorithm. We have a 5 process P0 through P4, then 3 resources A, A, B, C. A is having 7 instances, B is having 2 instances, C is having 6 instances. This is the current state. So already this has been allocated to each thread. This is the current request. This is the available. We find the safe sequence. Okay. Now T0 is requesting. It's not requesting any resources, so it can complete its execution. Then T0 complete its execution, the available after completing Z0, the available is same. Okay, after completing T0, the available is 0, 1, 0, right? So this is the available resources after completing, because this allocated will be added to the available. Now go for T1. The request of T1 is 202. It is not available now, so it will be in a wait state. Then go to T2. The request of the thread T2 is 000. So it is not needing any resources to complete the execution of T2. After completing execution of T2, these resources 0303 is added with available. So the available will become 3, 1, 3 after completing the execution of T2. Okay. Now T2 has completed its execution. Go to T3. Okay, the T3 is requesting 100. It is already available. So the T3 can complete its execution. Once T3 complete its execution, the available will become 5, 2, 4. This has been added to this, okay, this available. So then after completing T3, these resources have been available. Now go for T4. The current request of T4 is 002. It is available, so the T4 can complete its execution. After T4 complete its execution, the available resources, so this 2 will be added there. So 5, 2, 6. Okay. Now T4 also completed its execution. After T4 completed its execution, this is the available resource. Now which is pending T1. The request is 202, so it is available, so you can complete its execution. After T1 complete its execution, the available resource will become, you have to add this 2002, this one. So 7 to 6. After T1 completes its execution, we get this. This is equal to number of initial amount of resources. So now all the resources all the threads have been completed its execution. So the system is, this is the safe sequence. The system is in a safe state. There is no deadlock here. Okay. So we find that there is a no deadlock. Okay. So here for this problem, there is no deadlock. Okay. Now consider this, the next one. The T2 makes one more request for an instance of type C. So for type C, the T2 is requesting one more instances. So the request of T2 has become 001. Okay. Now there is a deadlock. We see. So again you start, this is the original available. You start with, so this has been new request of T1. So start with T0. So T0 there is no issue. Then T2, T1 cannot execute. T2, it's requesting, so it is not able. We don't have any resources, any instance of any resources. So T2 cannot execute. It won't release anything. Oh, okay. Yeah. So this is after T0 completed its execution. This is the available resource, but cannot meet it. So then go for T3. The T3 is requesting 100. It is also not available, so cannot be allocated. So T4, that resources is also not available. So already T0 completes T1. So T1 is also not available. So only T0 have completed its execution. The remaining threads cannot complete its execution due to unavailability of resources. So here there is a deadlock. There is no safe sequence. So here we find there is a deadlock. So here, so we need that order of uh, m into n square operations. We need to find whether the system is having the deadlock or not. Like that. So in the wait for graph to detect a cycle, okay, to detect. So for detect a cycle itself, we need that order of n squared operations we need. Okay, thank you.